In this module, we're going to talk about hybridizing recommenders. So far, we focused primarily on individual algorithms, one means of computing our scoring function or our ordering function. But different algorithms have different strengths and weaknesses. Collaborative filters work really well when you have a lot of data and where the items are relatively interchangeable. Content-based filters allow you to function even without a lot of user interactions around an item. In practice, we often combine multiple recommenders in order to try to capitalize on the strengths of different algorithms to produce better recommendations. If you're taking the honors track, you've already seen this a little bit in the previous. Rewind a moment. If you're taking the honors track, you've already seen a little bit of this back in course 2 with one of the assignments where we had you run a hybridized version of your recommender. So for a quick example, warm-up example, collaborative filters trained on ratings answer a question. If the user watches the item, will they like it? We don't have ratings for users the items didn't watch. For items the user didn't watch. And most of the items they didn't watch, they're less likely to like because most people, under most circumstances, don't run out to watch something they expect they're not going to like. There are exceptions, of course, but ratings are selected high. There's a different question that we can ask. Will the user watch it in the first place? And popularity is a really good first pass approach to this. So we could blend popularity with collaborative filtering to try to capture both of these ideas. Will the user watch it? And if they watch it, will they like it? And try to recommend things that the user is likely to watch and enjoy watching. So how might we do this? There's several different ways that we can hybridize recommenders. We can combine item scores. We can combine item ranks. We can integrate different types of data into a single recommendation model, and there's many other ways. We're going to see that more in some of the later videos in this module. One of the simple ways is a linear blend of multiple algorithms. So if we have, we can build our scoring function out of 2 inner scoring functions, and then we assign blending weights, these betas, to say how much we want to value each recommender's input. Oftentimes we'll have an offset just as a starting point for a nice linear model. And we can have 300, 400, 500 different recommenders that we put in. The Netflix prize challenge that was run a number of years ago, the winning algorithm of that was a blend of over 100 different recommenders. So we can do this kind of a linear blend of scoring. This is common and it's simple. We can extend this beyond just looking at constant coefficients to say the coefficient is going to be a function of some characteristics of the user and or the item. And this is called feature-weighted linear stacking. So in machine learning, we sometimes call these linear blends stacks. And the feature-weighted one means that the weights can change based on the feature. One really common feature to use in changing the weight is the number of ratings for the item or the number of ratings by the user. And this allows us to create a hybrid that emphasizes a content-based filter when the user or the item doesn't have very many ratings. And as the more ratings are available for users and items, it shifts the emphasis over to a collaborative filter. And it allows the blend to take into account the fact that different algorithms are going to be relatively strong or weak in different situations. These models are also very related to a family of statistical methods called hierarchical linear models. We can also combine item ranks, where rather than blending our S function like we saw here, we blend our O function. There's a few ways we can do this. We can mix ranked output, or we can convert ranks to positions or percentiles and treat them as scores. This works really well for blending in popularity. So to do that, we can say if we've got two recommendation lists, A, B, C, D, E, and B, D, A, C, E, and then we can say that the percentile rank here is we've got 1, 0.8, 0.5, 6, 0.4, 0.2. A equals 1 plus 0.4, B equals 0.8 plus 1, C equals 0.6 plus 0.4. Excuse me, A is 1 plus 0.6. D equals 0.4 plus 0.8, and E equals 0.2 plus 0.2, which is 0.4. So our final recommendation list is going to be B, A, D, C, E when we rank them in decreasing scored order, which B likes, or one recommender puts B at the top and the other puts B number 2. Putting B first makes sense. A is at the top and number 3, so putting it second makes sense. We've got D, which is at 2 to 3, C 2 to 4, and then finally both agree that E is at the last. So that's one example of how we can do rank blending. We can also integrate models. Several matrix factorization techniques can take into account both rating and content data. And this isn't hybridizing algorithms so much as it's hybridizing types of data. SVD feature factorization machines and generalized probabilistic matrix factorization are all examples of algorithms that can do this. A common pattern in some of these algorithms is that in addition to assigning latent feature vectors to item characteristics, so we have our PU, which is the user feature profile vector. We've got QI, which is the item latent feature vector. We'll also have some other, we'll call it Y sub K for some feature K, for some characteristic K. So it might be that you've got a particular latent feature for music albums from a particular label or from a particular producer or artist, and that allows us to get additional information about what latent features are going to be in play and share latent features across items that are related by some identifiable characteristic. And then there's various other ways you can envision putting feature data or content data together with rating data or consumption data into a single kind of model. In conclusion, mixing recommenders can let us capture the strengths of multiple different kinds of recommender algorithms. There's many different structures that we can do with this. And for some of the details, for example, we have this linear recommender. We need to find weights. The next module is going to be very relevant for the details of optimizing those weights and actually computing the correct or the best values to use in our hybridization strategy.